Missing data is one of those quiet killers in machine learning. You spend weeks cleaning features, tuning models, and then a single column with 20% missing values forces you into imputation. And imputation is a minefield. You're guessing at missingness mechanisms, introducing artificial discontinuities into your regression surface, and hoping your downstream model doesn't collapse. What if your tree algorithm didn't just tolerate missing values, but natively propagated them through the probabilistic structure of the model itself? That's exactly what recent work on probabilistic regression trees has tackled. Today, we're breaking down how these trees handle missing predictors directly during construction, why it matters, and what the empirical results actually tell us about predictive performance and computational cost. Let's start with the baseline. Classical regression trees, like CART, partition the feature space into disjoint regions and output a piecewise constant prediction. It's fast, it's interpretable, but it's rigid. The boundaries are hard, and the predictions jump abruptly. Probabilistic alternatives like PRTrees and soft trees soften those edges by assigning observations to nodes via smooth probability functions, instead of hard binary splits. But even those lacked a native way to handle missing covariates. Then came probabilistic regression trees, or PRTrees. They combine recursive partitioning with smooth probabilistic region assignments, and crucially, they come with a consistency guarantee. As your sample size grows, the estimated regression function converges to the true conditional expectation. That's a theoretical property you don't get with every smooth tree variant. But the original formulation assumed fully observed feature vectors. In practice, that's a major limitation. You could always run complete case analysis or impute first, but imputation breaks the smoothness PRTrees are built on, and it forces you to model the missingness mechanism, MCAR, MAR, or MNAR, which is rarely known with certainty. Misspecifying that structure can easily bias your downstream estimates. So how do you extend PRTrees to handle missing values without breaking the probabilistic framework? The authors introduce 3 distinct strategies, controlled by a single parameter. Each one preserves 2 fundamental properties: marginal probability compatibility, meaning unrestricted coordinates don't artificially inflate or deflate region probabilities, and probability conservation, ensuring that when a parent node splits, the total probability mass is exactly redistributed to its children. Strategy 0 is the uniform probability approach. If any value is missing, the model ignores all observed information for that split and assigns equal weight to both child regions. It's conservative, robust, and essentially says, I don't have enough information to decide, so I'll split evenly. Strategy 1 is the partial observation approach. Here, the model performs a hard compatibility check, using only the observed coordinates. If the observed values fall within the region's bounds, it assigns a probability of 1, otherwise 0. Smoothing is only applied to fully observed cases. It's a balance between robustness and information retention. Strategy 2 is the smoothed projection technique. This is where it gets elegant. Both the observation and the region are projected onto the subspace of observed coordinates. The original smoothing function is then evaluated in that reduced dimensional space. It makes full use of available information while preserving the continuous probabilistic structure. No imputation, no discontinuities, just a clean dimensional reduction that respects the tree's probabilistic foundation. Let's look at how this actually works under the hood. The core of PRTrees is the association function, which maps an input vector to a probability over regions. When missing values enter the picture, this function becomes recursive. At each node, the algorithm identifies which coordinates have actually been used in previous splits, and which of those are non-missing for the current observation. That set of indices defines the projection space. If the observation is fully observed, you use the standard smoothing function. If you're on strategy 0, or if no relevant coordinates are observed, you default to uniform assignment. If you're on strategy 1, you apply a hard indicator. If you're on strategy 2, you project both the data point and the region onto the observed dimensions, and evaluate the smoothing kernel in that lower dimensional space. The recursive definition ensures that probability mass flows correctly down the tree, regardless of which path the missing values take. There's also a product representation lemma that simplifies computation. If the smoothing kernel factorizes across dimensions, you only need to compute marginal probabilities for the splitting feature and scale by the parent node's probability. That's a massive computational win. Training a PR tree with missing values follows an alternating optimization scheme. You start with a root node and iteratively split regions to minimize squared error. At each step, you update the region boundaries, recompute the association matrix, and solve for the region weights using ordinary least squares. The smoothing parameter vector, which controls the width of the probabilistic assignments, is selected via grid search on an internal validation set. You're not just picking one sigma, you're testing multiple kernel families, Gaussian, student T, log normal, gamma, each with different shape or dispersion parameters. One key difference from CART is that a PR tree region doesn't need to contain any actual observations to exist. The association function measures compatibility, not membership. You still use midpoints of projected observations for candidate splits, but the tree structure is defined by continuous probability surfaces, not hard partitions. The process stops when you hit a maximum node count. The error reduction falls below a threshold or other constraints trigger. So does this actually work better than imputing and running CART? The authors tested it across 5 real-world regression datasets with varying missingness patterns. The communities and crime dataset had over 15% missing predictor cells, affecting nearly 84% of observations. The auto-MPG dataset had almost none. The results were striking. Across every dataset, the missing data strategy, the fill type, was the dominant factor in predictive performance. Changing the fill strategy shifted win rates against CART by massive margins, while swapping the smoothing distribution or proxy selection criterion only caused minor fluctuations. Strategy 0 consistently underperformed when missingness was high, because discarding observed information introduces unnecessary variance. Strategies 1 and 2, especially the smooth projection, capture the underlying structure far better. In high missingness datasets like crime and ozone, the probabilistic trees regularly outperformed CART. In low missingness or highly structured datasets like garment, the gap narrowed or flipped, proving that probabilistic flexibility isn't a magic bullet. It's a tool that shines when missing data actually interferes with the learning signal. Computationally, PRTrees are heavier. You're evaluating multiple candidate splits per node, running internal validation for the smoothing parameter, and reconstructing the tree multiple times. Student T-kernels are notably slower due to their heavier tails and more complex density evaluations. But here's the practical takeaway. Gamma and log-normal distributions often match or exceed predictive performance while running significantly faster. You don't need the slowest kernel to get the best results. What does this mean for practitioners and researchers? First, native missing data handling in probabilistic trees is no longer a theoretical curiosity. It's a viable, mathematically sound alternative to pre-processing imputation. Second, if you're tuning these models, stop over-optimizing the smoothing distribution before you've locked in your missing data strategy. The fill mechanism dictates performance, everything else refines it. Third, the computational cost is real but manageable, and you can easily trade kernel complexity for speed without sacrificing accuracy. This work opens the door to ensemble extensions, like probabilistic random forests, and more efficient split evaluation procedures. But even in its current form, it gives us a cleaner, more robust way to build tree models when the real world refuses to give us complete data. If you're working with incomplete predictors and tired of imputation artifacts, it's worth exploring the PRTree framework. The code is already available in R, and the theoretical guarantees make it a serious contender for production regression pipelines. Thanks for watching. If you want to dig into the math, try the package, or discuss how probabilistic trees might fit into your workflow, drop a comment below. And if you're interested in more deep dives into the latest statistical learning research, make sure to subscribe. I'll see you in the next one.